We concluded in the first part that the sigma-only bonding picture that is used for describing metal-phosphorus bonds is not fitting all the data that is available in the literature. We especially found that the metal-phosphorus bond lengths in phosphorus 3 complexes show that the bond distances are not as expected for a sigma-only bonding situation. And also the carbon monoxide stretching frequencies of complexes of ligands such as PCl3 and PF3 do not fit the data that you expect if you think of them as sigma donors. Now we have to ask the question, if we introduce the possibility of pi bonds in phosphorus ligands, will the bonding picture be able to explain all the effects? When X is electron withdrawing, it makes px3 a good pi acceptor. So computational studies suggest that d orbitals are too high in energy, and so they are not the ones which are responsible for pi accepting character. Is there another orbital on phosphorus which has the right symmetry and energy to accept electron density into the ligand from the metal? That is the question that we are going to ask. One answer that is given by computational chemistry and also theoretical chemists is the fact that the px bond has sigma star orbitals on the phosphorus, concentrated on the phosphorus, which can lead to donation of electron density into the empty orbitals on the phosphorus. These are empty sigma star orbitals, and if you put in electron density from the metals filled orbitals into these empty orbitals, you can have what is called negative hyperconjugation. And this will make the phosphorus ligand a pi acceptor. Especially if X group is very electronegative, the px sigma star orbital will have the right contribution from phosphorus in order to have good metal phosphorus sigma star overlap. Now we need to look briefly at the shape of these px sigma star orbitals before we conclude that the phosphorus ligands can act as good pi acceptors. If I were to draw the sigma bonds along the px bonds in the conventional way, I would localize it along the px axis. But in the molecular orbital picture, what you derive is a set of orbitals which are two are degenerate, are called the E set, and one is the symmetric low energy orbital, and these are shown here. The sigma bonds are marked. The sigma bonds are marked here. I will mark them in red. These are the sigma bonds, and they are of the E type. This is the E type orbitals, and this is the A type orbital. Okay, so this is A type and this is E type, or the degenerate set of two orbitals, or they are all bonding, and they have the character of a sigma bond. In the valence bond picture, you get three equivalent bonds. Here, those three equivalent bonds are symmetry deconvoluted to give you A and E set of orbitals. The lone pair is sitting on a HOMO, which is mostly localized on the phosphorus. So this is the HOMO orbital, which is localized on the phosphorus, and that's the donor orbital, which is responsible for the sigma bond between the phosphorus and the metal. The pi acceptor orbitals, we will label them in blue again, and these are the pi acceptor orbitals which are sigma star in nature. Turns out that the sigma star orbital will now be concentrated on the phosphorus. Just like the sigma bonds were concentrated on the X groups and more on the X groups than on the phosphorus. So that gave you these three sets of orbitals, which was more localized on the X than on the P. The sigma star orbital is more localized on the phosphorus. So as a result, when the phosphorus is pointed towards the metal, the sigma star of the px bond is capable of accepting electron density into these orbitals from the metal T2G set of orbitals in an octahedral system. So exactly like carbon monoxide, you have acceptor orbitals on the phosphorus now. Instead of the carbon on carbon monoxide, you have acceptor orbitals more localized on phosphorus on the px3 unit. So these are the two orbitals that will accept electron density. They have the character of the px and the py orbitals of the phosphorus. Earlier we were talking about the dxy or the dxz orbitals on the phosphorus. Now we are talking about px, the 3px and the 3py orbitals on the phosphorus, which are mostly localized on the phosphorus, although they are anti-bonding orbitals, sigma star orbitals. These are sigma star orbitals, but still they are localized on the phosphorus, and they are capable of accepting electron density into them from the metal. Let's briefly try to understand why in NH3 or a nitrogen-based ligands you do not have this acceptor property. If you look at the acceptor property of NH3, the bonding orbitals are localized on the nitrogen, and the anti-bonding orbitals are actually localized on the hydrogen. So NH3 is not going to be a good pi acceptor because the sigma star orbitals are now more on the hydrogen than on the nitrogen. So it would be a poor pi acceptor compared to pH3, where the phosphorus had greater contribution for the pi star orbital. Now we are ready to answer the question why PR3 groups are pi acceptors. It is because the sigma star orbitals on the phosphorus are having the right energy and the right symmetry to accept electron density from the metal filled orbitals. If you look at arsenic and antimony, they should also be pi acceptors. In fact, they are pi acceptors, but they are not as good as phosphorus because of the electronegativity differences that are present. You can work this out for yourself. You will notice that just as a difference between the two groups, the R group and the P in terms of electronegativity will make the electron positive element be the good pi acceptor. So we have answered this question already. Because nitrogen is more electronegative than hydrogen, in NH3 you do not have sigma star contributing too much to the nitrogen, and so you do not have acceptor property. Now I come back to this figure. Which I drew, and we will notice that this is now in accord with whatever we have explained up to this point, except that we are also able to explain why PCl3 and PF3 have stretching frequencies which are in fact higher, carbon monoxide stretching frequencies which are higher than MoCO6. This clearly explains that because PCl3 and PF3 are better bioacceptors than carbon monoxide itself, we have stretching frequencies for carbon monoxide which are higher than MoCO6. So MoCO3 PCl3 thrice and MoCO3 PF3 thrice have got stretching frequencies which are indeed very high in these are the values that you're having for PCl3 and PF3. Okay, so these are CO stretching frequencies and they're much higher than the base value of MoCO6, which is right here. The base value of MoCO6 is right here, and you have PCl3 and PF3, which are better pi acceptors, and so their stretching frequencies are lying in the other side of this graph. I had not discussed this earlier because everything else can be explained purely by sigma fx. But on the other hand, to explain PCl3 and PF3, you do need the pi bonding. So in order to help you understand how pi bonding is indeed present, and it is impossible to explain this unless you invoke the pi bond, I have kept this two data points away from the previous figure. Now you can understand very clearly that sigma bonding alone cannot explain the frequency changes in MoCO6 substituted with 3 phosphorus ligands. You need to have pi effects, and these pi effects are in fact very strong for phosphorus ligands, especially when the groups that are attached to phosphorus are very electronegative, especially like chlorine and fluorine. Okay. Now, I want to say that pi fx alone may not be sufficient. Polarization of the common d orbital also plays a role. In fact, the charge induced on the metal when you have a metal coordinated to another ligand, whether it is chlorine or bromine or fluorine, there is a charge which is induced on the metal. If I have MF, F is going to be delta minus and M is going to be delta plus. This delta plus will now affect the stretching frequency of the carbon monoxide which is attached to the metal. So bonding is dependent on the fact that you have charge on the metal. The charge on the metal makes a big difference. It is also dependent on the sigma bonding that is present from the phosphorus to the metal. It is also dependent on steric effects. Now, there are significant effects due to the steric influence of the R groups on the phosphorus. But before I end this lecture, I want to tell you that a significant amount of chemistry is developed through controversy and discussion. When there is a controversial uh, point about bonding or reactivity, it usually leads to better understanding of what is going on. In the case of phosphines, it is one example where the bonding nature was discussed for quite some time until it was understood that it is the negative hyperconjugation or the donation of electron density into the sigma star orbitals that is really contributing to the pi bonds in the metal phosphorus bond. And indeed, the d orbitals on phosphorus are higher lying virtual orbitals. What the computational chemists were saying was in fact right. It is in fact the sigma star orbitals that are contributing to the pi accepting character of the phosphorus ligand. Let me end this lecture by talking about the steric effects on the phosphorus atoms. In the early days when crystallography was still in its infancy, when crystallographic equipment was more difficult to obtain, many people relied on ball and stick models. The bonds were represented by a small stick, and the atoms were represented by balls of different sizes to represent the atoms. So these ball and stick models were used by Doleman to build models for phosphenes to figure out how much space each one of them required. And when he built models for different alkyl groups, he found that the angle that is required by, or the space that is required by the phosphine was in fact significant. He devised a simple method of drawing the angle subtended by the metal and the R group, which is indicated here on this figure, to be a measure of the space that is required by the phosphine around the metal. So you can imagine the metal as a sphere. Now, what Tolman did was to project this sphere on to the plane of the paper and converted the space required by the phosphine into two dimensions. And he obtained an angle that is subtended by the phosphorus ligand at the metal. So I'm going to draw the angle that is subtended by the PR3 group. This is the angle that is subtended by the PR3 group around the metal. And he found that if he can the use this angle as a measure, he can convert the volume that is occupied by the PR3 group into an angle by just projecting it onto a plane. And he obtained these angles. You'll notice that each of these phosphorus ligands occupies an increasing amount of space around the metal. In fact, when it comes to tertiary butyl group, you'll notice that the angle is 182 degrees. What that means is, if I put one PTBU unit onto the metal, the space that is going to be occupied around the metal is going to be almost one whole side of the sphere. 182 degrees is going to be occupied by one PTBU thrice group. So this seems to be almost unrealistic, but metal phosphine complexes can be dominated by steric effects, and Tolman was very quick to realize that this is an important parameter that can be used for measuring the strength of metal phosphorus interactions. In fact, the metal phosphorus bond strengths are affected by steric effects so much that if you look at this figure, you have dissociation of a PDL4 unit to give you a PDL3 unit and then subsequently to a PDL2 unit depending on the size of the ligand. If the ligand is sterically bulky, then the most stable complex is going to be PDL2. If the ligand is very small, like a trimethylphosphine, then it is going to be PDL4, which is going to be more stable. So this stability of the metal complex is in fact now dominated by steric effects and not by electronic effects. Palladium 0 is in fact a D10 system and it can accommodate 4 ligands. So when you have a sterically non-demanding phosphine, PME3, if I can call it that, if it's not demanding, then you form a PDL4 complex. If you have a very large group on the phosphorus, then it prefers the di-coordinated species or the PDL2 species. So you can see that the chemistry of the metal is going to be determined by the steric effects that are there on the ligand. The electronic effects can also play a role by having pi bonding, as in the case of PF3 and PCl3, but it can also be determined by the steric effects. Here is one more example. In this particular case, I have given a cobalt 1 complex, which is a D8 system. Usually, cobalt 1 would be D8. It would be a square planar complex because the square planar complex would be more stable compared to the octahedral complexes that can be formed. And because you have a, a D8 system, the D16 or the 16 electron systems are more stable, and you would expect it to be square planar. But this complex is in fact tetrahedral, and that is because the four ligands that are surrounding the cobalt are so bulky that they require more than a square planar geometry to stabilize it. It is surprising that in the case of the palladium, we also had a D10 system. It tended to dissociate and form the 16 electron and the 14 electron complexes by dissociation. In this case, it seems to prefer the tetrahedral complex rather than the square planar complex to accommodate the four bulky ligands around the cobalt. Now there is a interplay of steric, electronic, and other effects, the D8 versus the D10, the charge. So all these factors play a role, and you'd have to take into account all these factors in order to explain the fact that the palladium complex prefers to dissociate while the cobalt complex prefers to distort. This complex prefers to distort and form a tetrahedral complex rather than dissociate and form a linear complex or L2 system. Having said that both factors play a role, we should quickly add that the Dolemans angle is not just a steric parameter, but it is a stereoelectronic parameter. What Doleman approximated, because he was using ball and stick models, he could not measure the actual angle subtended by the ligand at the metal center. Instead, he used approximate bond distances, like the PM distance was fixed. So here I have indicated what it means to have a fixed PM distance. So whether you have a PF3 or whether you have a TPU3, this distance was fixed as 2.2 angstroms in order to achieve or in order to measure the bond angles. But in later days, crystallographic data was available, and so more realistic bond angles could be measured around the phosphorus atom. And so those distances are given here. But I want to say that these are very close to Doleman's cone angle. But just imagine when you have a short distance, the angle would be larger. So you can have a shorter metal phosphorus bond, then the angle subtended by the R groups would be larger. If it was a longer MP bond, then the angle would be narrower. So this Stolman's cone angle is in fact a strange phenomenon. It includes both a steric parameter as well as an electronic parameter. Now I want to talk about the bond distances as well. PF3, for example, I just mentioned to you. This has got a bond distance of 2.37 angstroms in the case of a molybdenum Ml5 complex where L is carbon monoxide. The phosphorus molybdenum bond is 2.37 angstroms. Whereas in the case of an adamantile system, where adamantile is a group which is surrounding the phosphorus, the angle is 2.479. So the MP distances can vary significantly, and clearly there are pi effects which are operating, which are making the phosphorus metal bond short here. But when you have a short bond, the angle can be large, even though you have only a small fluorine atom, the angle turns out to be 104 degrees. Whereas here, this is an adamantile phosphorus unit, and you have an angle which is almost equivalent to that of the PF3. Let me now wind up with this presentation. Phosphines, there are some key concepts which you have learned. There are pi bonds on phosphorus, but these pi bonds are not coming from the d orbitals. They are coming from the sigma star orbitals on the ligands. Secondly, we notice that there is a strong steric effect that is present on phosphorus ligands. This can be measured by Dolemans cone angle. I will also introduce to you another parameter called Nolan's buried volume. I mentioned to you briefly that the phosphorus ligand occupies a certain volume around the metal's coordination sphere. But in the days when crystallography was not yet popular, it was not possible to get the amount of volume that is occupied by the phosphorus ligand. And we had to resort to Dolemans cone angle. And Dolemans cone angle was a very good parameter. It was sufficient for a very long time. It is still used as a popular measure of the steric parameter or the steric influence of the phosphorus ligand around the metal center. Lastly, I have to mention that the charge effects are in fact important on the metal phosphorus complexes also. Although we have not discuss this in detail, the effects would be very similar because the same type of pi bonding is involved in phosphorus, just as in the case of carbon monoxide. I have to add one more factor to the key concepts that we have talked about. Electronic parameters can be adjusted by the R group by varying the electron withdrawing capacity of the R group. Like having a fluorine, you can have very good pi accepting property. But more importantly, you can have asymmetry around the phosphorus by having a chiral R group. The phosphine can in fact be a very good ligand for chirality induction in a reaction center. This has been utilized very significantly by chemists, especially organic chemists, for making chiral molecules. Unfortunately, PR3 groups with three different R groups can be chiral, but then they can also undergo the umbrella inversion. So as a result, one normally makes chiral R groups rather than making R1, R2, and R3 as three different R groups present on the phosphorus to induce chirality.